Welcome to the CFE Media and Technology Education Session, Critical Power Systems Expert Panel. I'm your moderator, Amaro Razgas with CFE Media and Technology. Let's get some basics out of the way before we dive into this topic. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand the fundamentals of critical power systems and learn some tips and tricks from industry experts. If you're interested in earning one AIA CES learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the resources option on the left side of your screen. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within this session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. And please don't forget, the Q&A starts in about 45 minutes. Here's a list of learning objectives. We'll touch on these during today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. There are also underlined hyperlinks for references and resources throughout this presentation. Let me introduce today's expert panelists. Tom Devine has spent 21 years in the consulting engineering field, with the past 17 years designing and engineering healthcare facilities. He's responsible for power, lighting, and fire alarm design for hospital and healthcare projects. Project experience includes hospitals, data centers, light industrial plants, and campus distribution systems. He has written a number of articles on standby generation and has presented at several consulting specifying engineer webcasts. Complex projects are Jeremy Geis's specialty and his favorite part of the job as construction manager for Henderson Building Solutions. Most of his projects are electrical, and it's certainly helpful. This master electrician also holds a Class A builder's license. Geis has more than 2 decades of construction industry experience managing turnkey electrical, mechanical, and plumbing systems design and construction. Brianna Robertson is an experienced electrical engineer with a demonstrated history of working in the building industry. Based in the Dallas-Fort Worth area, she primarily designs power, lighting, fire alarm for healthcare, and laboratory projects all over the country. She's been with WSP for about 4 years. Richard Vedvik has experience in the healthcare, education, commercial, and government sectors. His electrical engineering expertise includes lighting design, power distribution, emergency power systems, and fire alarm systems. For acoustical services, Vedvik collaborates with the design team for optimal architectural acoustical finishes, voice notification systems, and mechanical noise mitigation. He's helped develop in-house software tools and custom acoustics test equipment to assist searching for and solving noise problems and performing field measurements of equipment. He's a member of the Consulting Specifying Engineer Editorial Advisory Board and was a 2015 Consulting Specifying Engineer 40 Under 40 Award winner. It's my pleasure to work with some of the most well-informed power experts in the industry. Thank you, everyone, for joining this panel today. Let's get started. Jeremy, you're up first.
Today, what we're going to talk about here in this section is, what does the owner need? The owner's needs are very important to evaluate when looking at design. The backup systems, power backup systems, are no longer just a life safety measure. They're quite expansive nowadays, and there's a lot of different clients who have different needs within that. For example, hospitals right now, they have they're experiencing a large flux of patients, and it's forcing them to expand out into different facilities or expand within their own building to areas that did not have critical emergency power backup. So um, some clients will need their existing properties expanded upon. Redundancy is becoming very important too. As various clients lean on backup power, they really need those systems to come through and operate properly. There's a lot of communication, a lot of data that's flowing that was not present even 10 years ago. And the redundancy within those systems to operate flawlessly is very critical. Um, Budget is another big item with owners right now that needs to be discussed, because they will have expectations for how the system operates, and adding in the all the steps and equipment to make that happen can increase the cost quite a bit. Getting an understanding of the client's budget is going to help keep expectations in line with what they can afford to do and what they cannot afford to do. Then also looking at what type of business they're involved in. There's a lot of equipment that the clients will think of after the fact or after the system's online that they say, oh, I would have liked to have had this piece of equipment on here, because if this shuts down, it's going to compromise our end product, or it'll compromise, in the case of laboratory samples, that sort of thing. So making sure that communicating with the client up front about their business and how it's conducted will also help the engineer identify certain pieces of equipment or areas that they would want covered within that backup system. Moving on to the next slide, the critical challenges. Right now, these evolving market conditions emphasize clients' needs and expectations for performance. For engineers and designers, this can present quite a few challenges. Research shows that the most challenging aspects for firms right now are budget constraints, speed of delivery of the designs and the implementation of the systems, energy efficiency, staffing challenges to meet that particular demand, and integration of various systems. Controls right now are becoming a very large thing, and within building systems, and those control systems are sensitive to the transfer of power. The momentary loss of power will lock up control system. So there's a lot of systems in place, and they're very sensitive to these power transfers. Real quickly touching on some of the challenges as far as the budget restrictions. A good example would be hospitals. Right now, revenue is dramatically decreased in the industry, and their demand is increasing. They're going to be very restrictive on budget, and there's a lot of things that we're going to have to do within the industry to make sure that safety is not being compromised in the process. Clients are also incurring other financial burdens as their businesses change, as they alter other business practices, and that does impact projects that we do work on. Clients are also right now being very conservative with capital, trying to get them to realize is now a good time to spend money on these redundant systems can sometimes be a little bit of an uphill battle. Speed and delivery. Demand for quick yet precise systems and implementation are needed as the market evolves quickly. Clients are realizing an immediate demand, and sometimes they're realizing this month to month, and they're looking for systems to be flexible with it. They're also being conscious of budget. They're going back and forecasting much more frequently than what they have before. As part of that forecast, they would like to know, what are my costs going to be this month, next month, and that sort of thing. So they want these systems in place. They do want to understand what the costs are going to be up front. An accurate design is going to help make sure that that stays stable throughout. Energy efficiency. Critical power systems, capacity is always at a premium with them. Facility and or demand expansion is making energy efficiency priority. As we add more of these systems online, we're consuming more of that available space. So designs that are based around energy efficiency are going to help reduce the load on these redundant systems that we do have in place. In the quest of energy efficiency, clients are also relying very heavily on control systems and building management systems. Designs need to integrate and interact with these systems fluidly. Control systems, for example, do not do well with momentary loss of power. A blip that can occur in transfer of power will often crash a control system and prompt it to reboot. With buildings that have control systems, generally a UPS system that covers that BMS will prevent this and is oftentimes absolutely necessary. So that is stuff to consider within a design as well. Last thing I'll hit on briefly is the staffing challenges. As these projects and as the owners want to rush these designs and implementation throughout the process, they want to get these projects into bidders' hands to start with. As soon as they get the bid process taken care of, they want to get the installation going. So to meet the rigorous demands on timeframes and that sort of thing, firms are going to have to staff up with skilled, qualified employees. The preciseness and reliability of these systems overall is key. Having the skilled staff on hand that can quickly respond and do it accurately has been absolutely important in the industry. I will pass it off.
Thanks, Jeremy. We all are very much aware that codes dictate much of what we can and cannot do within buildings and structures. Now, some of my favorite codes are listed on this screen. Of course, we're all familiar with NFPA 70. The National Electric Code has a variety of aspects that affect emergency power. We have sections specifically dedicated to generator and fuel systems. We obviously have Article 700, which has a wealth of information, especially 700.10, which gives us our guide map for how we need to arrange a lot of the distribution and some of the aspects of how we deliver power throughout a facility. And of course, 517, healthcare, is just a wealth of information telling us how we can and can't use an emergency power system and what we can and can't serve on the variety of branches. We'll touch on that a little bit later. Speaking of healthcare, NFPA 99 is a fantastic roadmark and guide for all of us to use for emergency power systems, what has to be on the generator. And specifically, it goes into levels of redundancy based on critical care types, whether it's an operating room or an ICU, or maybe even just a general exam room. It's going to tell us what we can and can't put on that emergency power system. Now, we don't necessarily think of NFPA 101 as being an emergency power doctrine, but it certainly has aspects associated with egress and elevators. And Chapter 7 is an excellent resource for designers to read through so they understand what parts of the building, the life-saving aspects of getting people out of a building safety, they should be considering in their emergency power. Now, my personal favorite is, of course, NFPA 110. Besides giving us a very clear delineation of what we have to consider for the runtime and the outage duration by the class or type specification for the EPS and EPSS, it also tells us where we can and can't put things, the mechanical and the environmental requirements associated with that life-saving equipment. Now, Tom's going to go into a little bit more detail on when we look at buildings in the IBC.
Thanks, Richard. I'm going to look at some of the things that the International Building Code, or IBC, requires standby or emergency power to support. egress lighting, and that would include exit signs, the fire alarm, horizontal sliding doors that are used for egress, and radio coverage that supports first responders. And it's worth noting that all of these things could be supported by battery power systems. They don't have to be supported by a generator. It's also elevators when they're part of an accessible means of egress, and smoke control systems for some of these specific occupancies. High-rise buildings get special consideration, and wherever elevators, or wherever there are high-rise buildings, elevators are required to be on emergency power or standby power. Group I2, the IBC does not directly address their emergency power requirements. Instead, it defers to NFPA 99, the hospital code. Group I3, which is for detention facilities, it requires power-operated doors and locks to have standby support. And then in Group H, which is high hazard occupancies, the emergency alarms that support high hazard and the requirements of the International Fire Code have to be met. And finally, air-supported membrane structures, semiconductor fabs, and underground buildings have to have standby power regardless of what their configuration might be like.
So now that we know where emergency power is required, we can go into the different types of sources that we will provide. First and foremost are generators. This will pretty much be the majority of the emergency power sources that you'll see. There's different types of fuel. We'll start with diesel. This will be the most common fuel source used, especially in larger generators. You can store it on site and it's easily accessible. Another is natural gas. This one is requested, but in critical care facilities like healthcare, you are required to have on-site fuel storage, so natural gas does not meet that requirement. Also, in areas where seismic zones C or greater, you could have an earthquake that could crack a line, so that's something to consider with natural gas as well. Propane and gasoline are typically just used in smaller generators, and those aren't typically used as frequently in critical facilities. Next thing to consider is location. This one's probably the most important. Generators can be located indoors or outdoors, and there's a lot of different items to consider when you are locating your generators. Air intake and discharge and exhaust are all items that need to be coordinated with your mechanical engineer, as they greatly affect their design, especially if you locate your generators indoors. Your generators have to be located within a certain distance of walls. You have to have certain louver sizes. These are all items that have to be designed on a case-by-case basis. Next is acoustics. If you do need to locate your generators indoors, you need to consider the location within the building that you want your generators to be. You don't want these on the same level as your ORs in a hospital or near offices where people will be there all day. And then if you need to locate them on the outside, in the exterior of the building, then you need to consider coordinating with your city and your AHJ on nearby neighborhoods, apartment complexes, and other buildings to meet the acoustical requirements there as well. Next is installation and maintenance. This is just planning how your generators will get in and out of the space, how they will be maintained by both the facility, and if you need to exchange out a generator in the future. These are just items to maintain certain clearances and distances that are easy for this process. Next is fuel source location. Fuel source can be located above ground or below ground, but it's important to remember that if your generators are located indoors, for instance, and your AHJ requires fuel sources to be located above ground, you more than likely will need some sort of transfer or day tank, because you have to maintain a certain distance between your fuel source and your generators. And most of the time when you have to locate your fuel source above ground, it cannot be located indoors because there are certain requirements on maximum capacity allowed inside of a building. And then finally is egress. This was touched on a little bit earlier, but for generators and ATS locations, you need to abide by certain egress rules for obviously getting out of the room, and then lighting and battery backup power. Next is voltage. This one's mainly determined, honestly, by the engineer. You can look at the size of your building and the emergency power system that you have and determine if you can have a 480 volt system, or if you feel you need to move it up to medium voltage, which medium voltage is typically used in larger facilities and campus style setups where you have to serve multiple buildings. Last is quantity. If you have enough emergency power to require multiple generators, you need to have some means of paralleling them. Most of the time we design around a paralleling gear, which is an all-in-one system. It has a switch gear, it has metering, it has controls, and has the ability to parallel your generators. If somehow the owner doesn't want that, or if it's not in the budget, there's another option of something like a power command, which is basically it comes with the generators and it still allows them to talk to one another, but it's just more remote at the generator location. If your facility is smaller to where you feel you can only you can serve the entire facility with one generator, then you have to consider a temporary generator tap in case that generator needs to go offline and you need to work on, you need to have means of still providing emergency power to the building. Finally, I just want to touch on a UPS. This is a supplement to generators. This is mainly if your owner feels that they have equipment that they absolutely need to be on in any case, and they don't want to wait that a little bit of time between when the power goes out and when the generators kick on. They want to have that source readily available. A lot of times this occurs in healthcare when it comes to imaging equipment or certain ORs. They just don't want to risk the chance of having to redo a procedure, or they don't want to risk a patient's life. The types of batteries that we mainly see with that is lithium ion and lead acid. As of late, lithium ion is mainly designed around. The price of it has gone down over the years. It's smaller, it weighs less, it's easier to maintain. So that one's more of a choice over lead acid nowadays. And then finally, if UPS isn't needed in your facility, whether you don't have anything imaging wise, or your owner just doesn't feel the need to have a central design or central system for UPS, there's a local option. A lot of IT racks require UPS now, and a lot of times we either provide it on the full UPS system, but if that's not needed, then you can design around a local system and talk with your IT vendor to ensure that you're providing power to that locally in those rooms. These are all items that need to be discussed with your owner as early as possible in the design, because these affect multiple trades and affect your overall emergency power system.
We're going to talk about the term mission critical and what it means and how it got into the facilities industry. It originally applied to Department of Defense facilities and came into real use there in the late 90s. Like a lot of terms, it migrated from DoD to the building industry. And when it first entered the industry, it was initially almost always used to describe data centers, to the point where mission critical and data centers were practically synonymous. Since that time, it's taken on a broader and maybe a more sensible meaning, and it's to mean anything whose loss would cause a disastrous consequence for the owner or for others. That might be loss of life, serious injury, it might be a contractual default or lost revenue for businesses. Some examples, in government, we might have dispatch centers, air traffic control, or other kinds of command centers. Where the protection of human beings is involved, we would look at hospitals, laboratories, which may be involve experiments with noxious substances that can't stop being evacuated, and manufacturing facilities where a loss of power might cause some kind of industrial accident. And then in business, we might see it also as banking centers, trading, and again, of course, the usual suspect, data centers.
Thanks, Tom. Now, when we're talking about types of power systems, we've been including in discussions on UPSs and generators, how those break down and where you need to locate them. Within NFPA 110, sections 4 and 5 both define the EPS, or emergency power system, and the EPSS, emergency power supply system. Now, it's important for designers, engineers, owners, facilities to understand the difference between those two aspects. So, for your benefit, we have a graphic here. And this graphic shows you that the EPS includes the generators, or UPSs, however you want to parallel them, and whatever connects them together. So that could be paralleling gear, or simply it could just be a busway. Once we get to the overcurrent protection devices, or circuit breakers, or fuses, that then is the delineation between the EPS and the EPSS. So from now, we can see that the EPSS includes the circuit breakers and the transfer switches and the cabling. Once we hit our transfer switch, that defines our branch, whether it's going to be life safety, critical equipment, or if you're under Article 700 and you're not 517, then it's going to be emergency, legally required, and optional standby. These branches set up based on the level of importance. So we have life safety or emergency traditionally is going to be your alarms, anything that's egress related. When we get to legally required, we're going to be more fire protection, fire's life-saving systems. Critical, of course, in healthcare is going to be all of your 10-second loads for patient care and anything that supports the patients. And then you get to equipment and optional standby, where you're adding in everything else that allows that building to function. And we're going to talk a little bit later about what that means in an application. But Jeremy, I believe you have some more to add to this.
Absolutely. Thank you, Richard. Something that's important to keep in mind too within these systems is the level or the priority level. As Richard mentioned, level 1 or priority 1 being life safety and needing to transfer within 10 seconds is a code requirement. After that, you do encounter situations where certain equipment will need to be brought up. Even if it's not code required, it's going to be client required. Identifying these levels of priority will not only help identify how loads get added onto the generator systems, but it also helps identify how we shed those loads off the generator systems, either in the case of an emergency where, say in the case if you have multiple generators and one of them goes offline, you need to shed that load off. The engineer will need to identify which loads need to come off first and how it's going to impact the operations of that facility.
All right, so let me talk a little bit about some research that we completed in August 2020. We researched information about electrical engineers, power systems experts, and we looked at what types of technologies they felt would be in demand. And this was probably some of the usual suspects that you anticipated. Of course, we're talking about emergency and standby power here, but there are some additional products and system types that popped up that we thought were pretty interesting. Jeremy, I think you had some input here.
Absolutely, and as you'll see, no surprise, emergency and standby power systems are at the top. Right now, the demand for critical power systems is steadily increasing each year in all industries, most notably in industrial, manufacturing, warehouses, offices, and healthcare facilities. Reliability is also being pushed to the forefront as well. For example, as the consumer market demand for online purchasing increases, so does the logistical infrastructure of getting products from factories to the end user in an accelerated pace. Within that, an interruption of production due to power loss can result in a client losing large sums of revenue, and oftentimes by the minute. Warehouse distribution lines ceasing to operate upon power loss can cause critical issues with logistics in moving products to the market. Again, this is going to cost the client and everybody within that chain a lot of money. Given the current state of economic conditions relating to the pandemic, offices are being utilized in different ways, different capacities, and all of a sudden communication, data transfer, and having that be done stably it's never been more paramount than it is today. Hospital critical care patient loads are significantly higher, and provoking that is rapid expansion of facilities as they try to accommodate these loads of patients, and the systems need to be able to adjust to that as well. This also increases the demand for expansion of power backup systems, these critical areas. So it's not surprising to see that on there. I think everything that's on there is something that we probably all encounter pretty equally across the industry as of late. So I think those numbers will be very important to pay attention to.
Yes, and as you just mentioned, Jeremy, we're noticing project demands changing based on COVID-19. So maintenance, repair, and operation, no surprise, that rose to the top. New construction fell to the bottom. The pandemic has changed the way electrical engineers and their projects have been proceeding. So I think this is kind of an interesting take on what's going on right now.
It is, and as facilities and businesses try to grapple with how they're going to handle their budgets, they are trying to take what they have and utilize as much as possible. Within that, they're not quite as anxious to simply go out and replace stuff with new items or new equipment. So maintenance becomes a much bigger concern. Keeping these systems operational for the time being is really where a lot of facilities are focusing. And hopefully that maintenance is taken care of well enough to the point that catastrophic failures do not happen, but that is something to be mindful of, is what level of maintenance are they being provided. Otherwise, again, taking existing spaces, expanding them out, and repurposing them, it has caused some challenges within the industry, whether it's egress from an area that was not designed originally to say house a bunch of employees, or whether it's a case of hospitals where they need to expand their patient beds and the operations within that. So.
Yeah, and next we looked at the types of projects that are anticipated as COVID-19 continues to affect the industry. Office buildings was right at the top, which was a little surprising, but next, industrial or manufacturing facilities, that really did not surprise us because we do anticipate these to continue growing and expanding, especially with electrical and power systems.
Thanks, Samara. So let's talk about something that I've been seeing more often lately, and that is existing hospital campuses that are trying to go through the maintenance and the retrofit scheme. They're running into a primary issue of their emergency power supply system, their EPSS equipment, not being A, modern, and B, currently legally located. So let's say you have a project or a renovation and you need more critical power. You want to go back to an ATS. Turns out that ATS is old. You're like, wow, we should probably replace that with something more reliable, except now we pay attention, it's actually located in the normal service equipment room. Essentially, what code's trying to do with redundancy is make sure that a catastrophic failure of the normal equipment does not render all of the EPSS, your transfer switch and your emergency distribution, useless. If you have a catastrophic explosion, that's all metallized and that's aerosolized metal that can take out all the equipment in the room. That's why NFPA 110 says for level 1 system, you have to have a separate space there. Now, when it comes to actually replacing your transfer switch, you have a couple options. You can either reuse the existing cabinet as a junction box, and while that's a legal idea, it kind of comes back to the previous conversation about making sure that we're not going to make our emergency power system vulnerable to failures on the normal side. Instead of that, we could always refeed the load itself, whether it's panels, motor control centers, distribution equipment, but that might require running through an existing facility. It could be more costly, and it might be hard to get to some equipment that's actually buried within a facility. Another option is intercepting that feed and having a junction box. Now, all of these require outages. And you can ask yourself, how long is it going to take? It might be 30 minutes. It might be 2 or 3 hours. It really depends on the number of feeds that have to be physically moved. And you could say, well, temporary power will solve that problem. But even that is a 10 to 20, maybe 30-minute outage to physically remove cables and land them someplace else. These are all conversations you have to have with the entire facility really early on. Now, when we talk about the reliability and redundancy of generators, we have to talk about priority. If I have a big enough system that I have multiple generators, when do they come on? If I have 20 transfer switches in a campus, they can't all hit at once. I have to stagger them. You're going to stagger them in coordination with your generator manufacturers for running software on load dip, and essentially understanding that a frequency dip and a voltage drop is one of the things that's going to cause a generator to signal that it has a problem. So what I have here really quickly for your reference is an idea of how you're going to design your system and start to plan when can certain transfer switches be brought online. What is their priority? And then those priorities are contacts that are going to inhibit the transfer until the paralleling gear says that it can transfer. Now, if your paralleling gear is a long ways away from your transfer switch, you need to understand that this could actually introduce a lot of cost and complexity in renovation projects when you're adding switches, and now you need to change or modify the existing priority scheme.
Commissioning power systems in a facility is extremely important. We go through and we can have the perfect design, and whether or not it got installed that way, whether or not all the components are going to operate together, is largely unknown until it's tested. You don't want that first test to be when they really need to use the system. So commissioning throughout the process and at the end of a project, making sure that all those components are communicating and working flawlessly with each other is extremely important. Component testing, we want to know that the ATS is communicating with the generators. We want to know that the startup functions are initiating the generators and that sort of thing. The emergency stops are working, and all those little pieces that that we need to have functional in various events. After that is when you bring everything online together. As you do the individual component testing, what you are not testing are these 6, 7 different areas and pieces of equipment, are they all going to come together, and are they going to dance nicely together? This end test, sometimes referred to as a black site test, will vet that process out. Within commissioning, all the way down to the black site test, documentation is critically important. You want to know exactly what numbers you're getting. It might be voltage. So when the generators come up, do you have voltage sag anywhere? Are they over voltage? That sort of thing. Sometimes seemingly not getting readings that are, don't seem to really stand out. They will stand out later on down the line in interaction with different equipment, and having that data be able to go back to is very important on that. You're also providing data to the owner, to the client, saying that here is our proof that this system is working properly, and that if anything does come up down the road, that documentation is there to protect everybody's best interest and help troubleshoot that situation at that time. The engineer and the designer should absolutely be part of the commissioning process on this. Again, it is their design. They needs to be seen through to the end to assure that installation, everything was done correctly. A lot of times on sites, just simply having the engineer there, that engineer can quickly answer questions and keep the process moving. The client, general contractor, and other contractors will greatly appreciate that as well. That goes a long way with the client, and they'll remember that for the next project. Within that, the engineer can also assure that loads that need to be added, shed, that sort of thing, are being done in the correct sequence. And again, it provides a basis of control for the project. And then last, the control systems on it. Commissioning of the control systems is huge right now. With control systems being involved in so many aspects of buildings operations, again, they're very, very sensitive to the loss of power, the momentary loss of power. So because those control systems are so central to the heart of a facility or a building, we want to make sure that we're paying attention to those as well in the process.
Thanks, Jeremy. So we've talked about a lot of equipment inside the building, but there's a little bit more to it. We got to think about how our power is actually getting to our building, getting to our main service equipment that will then serve our entire building. In this specific case, this is a site plan of a facility where we are adding a 500,000 square foot building. They're in the middle of the screen, and the existing campus feeds for all the other buildings were going right through the middle of it. So we had to relocate all of them, and we had about 7 or 8 different building feeds that we had to relocate with the addition of our new building. So the importance of understanding the outside portion of getting everything into the building, I think, is very important. I think everyone kind of forgets that this part of it, because it's not usually as complicated as what you see on the screen, but there are a lot of items to consider. So in this specific case, at the bottom part of the screen, you see where we had to route through an existing garage, which was very complicated. And then we had to break apart into 2 different duct banks. One will actually be where we had to reroute the existing utility service coming in, and then the other one, the larger one, going on the outside, is where the feeds are to the rest of the building. And then you can see where there's a couple snapshots of the duct banks where we had to calculate how far underground they were going, how many ducts we can get inside of each duct bank, and then how to space them apart. All of these are extremely important, especially for this specific case where we had a campus feed and it was medium voltage feeds. So they produce a lot of heat. So this is very important. You have to go through this calculation process to ensure that you are spacing everything out appropriately so they can service the equipment that is required to meet it. So in this slide, it's actually the same building, but I'm showing a civil plan to give a better idea of how complicated site coordination can really be. In this case, we kind of color coded everything with the dark purple being the existing electrical that you just saw a minute ago, where we relocated that around, and then we color coded all the other utilities that needed to be rerouted and go through the coordination process as well. We have, steam, sanitary, chilled water, comm, a little bit of everything. And this is honestly just what had to be relocated. It's hard to see in the background, but there's existing lines that are actually grayed out that we didn't have to relocate, but they're still within this boundary. And so it's important to understand how much we need to communicate with the other disciplines when looking into the site plan, because you have to also coordinate how this will all be installed. Like Richard mentioned earlier, you have outages. And so during this process, since we had to relocate feeds for 7 buildings, we have to coordinate all of those outages, and the importance of coordinating that with the facility and making sure the owner is aware of the impact for that and how they plan on addressing that and what time of day they want to do all that. So all of this is extremely important, and having numerous coordination meetings to ensure that we don't, especially for critical care facilities like healthcare, that we don't cause a problem, and everyone is aware of our outages and when they will they occur.
I'm going to talk about a case study of a hospital in Houston that was flooded in 2001 and did a lot of flood remediation and hardening after that. The event that started the project was Tropical Storm Allison in 2001, in June in Houston. It dropped 40 inches of rainfall over a few days and caused widespread flooding throughout the whole area. In this hospital, there were 2 normal power service entrances that wound up about 20 feet underwater. The generators themselves stayed dry, but the paralleling gear was about maybe 10 feet lower than the generators, and it was inundated. So there was no way for the power to get out of the generating sets. So the facility lost both normal and standby service and wound up having to evacuate. And that itself was kind of a heroic story. The initial phase was recovery to get the hospital back in operation. And to speed things, the strategy was to rebuild everything in place. There was the cleanup, the assessment of the condition of the remaining of the equipment. Major equipment like the service entrances and a lot of transfer switches were reconditioned and reinstalled, and smaller equipment was just replaced. And the project for recovery took about 5 weeks, and the hospital was out of service during that time. Now we look at the remediation, which the project established a reference level that was 2 feet above the actual flood level. There were a number of entities involved in setting that level, and each one added a few inches to what the previous one set. And so by the time it got to us, we had 2 more feet. Our design rule was that nothing in the hospital that was below the reference level would serve anything that was above itself, so that if a piece of equipment got inundated, we didn't lose anything above it. Here's a short list of some of the construction items. We had to come up with 2 new central plant spaces. We installed new service entrance and paralleling gear at about 20 feet above the reference flood level. The generators stayed where they were. They were barely below that level and were protected with barriers. And then we did risk analysis of critical systems, where we asked what can go wrong and how can we ameliorate it. An example might be generator fuel pumps. To ID, for example, what their elevation would be, so that if the generators were dry and my fuel pumps were wet, we'd still run out of power in about 30 minutes. Challenges were collecting information during design. It was a working hospital. Some of the drawings had been destroyed by the flood, and it was over 1 million square feet of facility and a campus. that spanned over 50 years. And then coordinating outages during construction, as Richard mentioned, because everything in the hospital was disconnected from the original services that were below flood and reconnected to new services above. Here are what the results were. Allison was supposed to be a 500-year flood, and then 16 years later, we got a better 500-year flood. Hurricane Harvey dropped 60 inches of rainfall in the area. It beat Allison by 50%. And this is a quote from time.com, a major news organization. It says the facilities were ended up in a moat. They were surrounded by impassable streets that were flooded with water and no one could get in or out. But for the patients and staff inside, it was pretty much business as usual. And the reality is that it was not the electrical design that really kept this hospital going. The barriers worked. The first line of defense kept everything dry, and nothing happened inside except that we had to wait for deliveries.
All right. Well, thank you for that great information. And thanks to our subject matter experts, Brianna, Jeremy, Rich, and Tom for this presentation. Questions will be answered in a live question and answer session on October 8th at 12:45 p.m. Central, 1:45 p.m. Eastern. Participate in the live Q&A session with your Zoom invite details. These details can also be found on the Additional Resources tab on the left side of the screen.